Hi everyone, I'm Ashmi, the technical content creator of Bloq Quantum. So today we are going to explore one of the most exciting applications of quantum computing, which is the digital quantum simulation. So our implementation is inspired by the Nature paper, which is the digital quantum magnetism on a trap and quantum computer. So while that work used the programmable quantum processor with 56 trapped on qubits in order to study this complex quantum dynamics, today we'll just focus on the core idea behind it. So using just a 2-qubit circuit on the block platform, we'll see how a quantum Hamiltonian can be translated into a quantum circuit using characterization, and also even if it is a smaller system, it still captures the same fundamental simulation principle. And we'll see how it works. So, why do we actually need quantum simulation? Many physical systems, such as the quantum magnet superconductors and then strongly correlated materials, are all governed by this principle of quantum mechanics. So, accurately describing their behavior itself requires representing a quantum state whose Hilbert space grows exponentially with the number of particles. And this makes exact simulations computationally intractable on classical computers. So in 1981, Richard Feynman proposed an elegant solution. So instead of simulating the quantum system using the classical hardware, we should use a controllable quantum system to emulate the dynamics of another quantum system directly. So this research that inspired this tutorial demonstrates this concept on a much larger scale. So the authors here implemented a programmable digital quantum simulator using 56 trapped ion qubits in order to study the transverse field Ising model. So Ising models are usually the fundamental models in condensed matter physics. So by repeatedly applying carefully designed quantum gate sequences, they were able to investigate collective spin dynamics and also the many body quantum behavior that are extremely difficult to study using the classical computation. And in this tutorial, even though we won't be reproducing the full experiment, we'll just create the fundamental circuit building block on block in order to make these simulations possible. So everything begins with the Hamiltonian of the transverse field Ising model. The first term here represents the interaction between the neighboring spins. And in a quantum circuit, this interaction is implemented through a ZZ evolution, which we'll realize using a sequence of C0 and RZ gates. And the second term here represents the transverse magnetic field. So physically, this field tends to flip the spins, which introduces quantum fluctuations. And in our circuit, this effect is implemented using the Rx rotations, which is applied to each qubit. And together, these two terms would describe the dynamics of the system we are trying to simulate. So the Hamiltonian describes how the quantum system evolves continuously over time. However, the quantum computers operate using discrete gate operations. So to bridge this gap, we use a technique called trotterization. And instead of performing one continuous evolution, we divide it into many small time intervals. So each interval here is approximated by a short sequence of quantum gates known as a trotter step. And repeating this building block allows the quantum circuit to approximate the evolution, uh, the evolution of the original Hamiltonian itself. So basically, in this Nature paper, they have implemented it, as I told before, using 56 qubits, but we will be using only 2 qubits. And they have simulated the full spin lattice. But here I'll be showing just with one interaction, and then we'll be seeing for one proto step, two proto step, and then three proto step how it works. We are just demonstrating the same simulation technique, but not trying to reproduce the complete experiment. So now let's move to Bloq platform and see how we can build this circuit. So this is a sample which I'll be building. So we'll first be beginning with the 2 qubits initialized in the ground state, and next we'll be applying the Rx gates to both the qubits. Representing the transverse magnetic field, and in order to implement the spin-spin interaction, we'll be using the C0 as its C0 sequence, which realizes the required ZZ evolution. Finally, we'll apply another layer of Rx rotations, completing one proto step, and then measure both the qubits to observe the resulting quantum state. And also, we'll be repeating this same blocks in order to reproduce the second and third proto step. So after running the circuit, Bloq will provide both the state vector amplitudes and the measurement probabilities, which I'll be showing in some time. So the state vector represents the complete quantum state, including the amplitudes as well as the relative phases in of each of the computational basis state. And when we perform a measurement, those amplitudes collapse into probabilities, giving us the likelihood of observing each basis state. So even with only two qubits, we will clearly see how the Hamiltonian evolves the quantum state through a sequence of quantum gates. So we are on block, and now here let me create a new circuit. So first I'm applying the RX rotations to introduce this transverse field. So yeah, and then another RX. So then after this, I'll be implementing the Z interaction using a C naught, RZ and C naught decomposition. So we have this C naught gate here, and then the RZ, and then the C naught gate again. So after this, so this C naught RZ C naught sequence implements this exponential ZZ evolution operator used in one trotter step of the transverse fielizing Hamiltonian. So finally, I had another RX layer to complete one trotter step. So this is before measuring both the qubits. So yeah, let's see the probabilities. So yeah, this one is the measurement probability distribution, and this is after executing 1024 times of the shots. So now this is for one trotter step, and we find that the probability is almost 50-50. And this is the state vector distribution. So now So now let's implement this for three data step, and here I've written the code and then obtained the circuit. So yeah, these are the circuit codes, and now so this is the probability measurement probability distribution graph. So this was obtained after executing your circuit 1024 times or shots. So after executing three trotter steps, block basically displays these two complementary views. The first one is the probability and next one is the state vector. So the state vector shows how the probability amplitudes before shows the probability amplitudes before measurement. So here both the magnitude and the sign of each amplitude carry information about this quantum state. So as we see here one amplitude is negative. So this represents a relative quantum phase rather than a negative probability. So once we perform the measurement, these amplitudes collapses into the probability distribution, which is shown in this view. So in our simulation, the repeated trotter steps have evolved the quantum state such that the state with one basis state has the highest probability. This illustrates how the Hamiltonian drives the system's dynamics over time. That's it for today. Thank you.